And our next speaker is Dr. Reza Ganjdanesh. He's a research associate in the Hildebrand Department of Petroleum and Geosystem Engineering at the University of Texas at Austin. His research areas include unconventional resources, reservoir simulation, phase behavior, CO2 sequestration, and H2 storage. Reza, please.
Thank you, Dr. Sapanuri. Let me share my screen.
Did you share with sound?
Yes, I did. Yeah. Do you see my?
Yes.
Okay, good. Hello, everyone. My name is Reza Ganjdanesh, and I'm going to talk about the CO2 storage and energy production, the opportunities and challenges. So I'm going to talk about the CCUS opportunities, mostly in the Texas, and about the projects that we have been involved in the past decade or more. So I'm going to give you an overview about 3 different projects, as much as the time will allow me. The first one that I'm going to talk about is about the CO2 storage and geothermal and methane production from deep pressure geothermal aquifers in US Gulf Coast. The second topic will be CO2 enhanced oil recovery in unconventional reservoirs. And the third one will be CO2 enhanced oil recovery in mature conventional reservoirs. So the first one about the geopressure-geothermal aquifers in the US Gulf Coast. These aquifers are abnormally pressured aquifers, and their depths are exceeding 10,000 feet. And they are mostly saturated or oversaturated with methane. And the methane content can be easily in the range of 30 to 60 SCF per barrel of brine or even more. And the temperatures are mostly exceeding 300 degrees of Fahrenheit. So there has been several different studies about the estimated reserves of methane and geothermal energy in these formations. There are like different numbers, big ranges, but all of them are more than 1,000 TCF of dissolved methane, which is a very significant number. And also the equal amount of geothermal energy that can be produced from the brine. So the main formations in the Texas Gulf Coast will go into the deep area of Frio all the way to the Wilcox formations below the depth of 10,000 feet. So there has been in the 70s and 80s, Department of Energy had an extensive study and research on this topic, and also even they had several wells drilled as wells of opportunity to study and test the production of energy at the time from these formations, where at the time it was mostly focused on producing methane. So the data was collected from more than 4,000 wells in just the Texas part. And these are the average pressure and temperature versus depth. So the average of all these wells above 10,000 feet is mostly in the range of hydrostatic gradient, but below 10,000 feet in this area of Gulf Coast, the pressure will start to grow rapidly and go below above 10,000 PSI. So the increase in pressure and temperature will add into the solubility of methane in brine. So the solubility of methane in the geopressure condition is almost twice as the solubility of methane in hydrostatic condition. But the other very important aspect of these formations are very high temperatures. So again, below 10,000 PSI, 10,000 feet depth, the temperature will grow rapidly and easily go beyond and above 300 degrees of Fahrenheit, which is 150 degrees of centigrade. So here is like a map of all those 5 formations that I was talking about in the Texas Gulf Coast, from the Wilcox to at the bottom, all the way up to the lower Frio. And as you see, there are a lot of areas that temperature can easily go above 200 degrees of Fahrenheit. So above 150 degrees of centigrade, I'm sorry, changing between centigrade to Fahrenheit, but above 150 degrees of centigrade, the heat can be converted to direct electricity in a geothermal power plant with an efficiency of 7 to 10%. But if the temperature is below 150 degrees of centigrade or 300 degrees of Fahrenheit, that heat can be directly used for different purposes. One of the purposes can be the capture plant. So in the study that we were doing at the time, like designing a closed loop cycle of producing the fluid from these reservoirs. So the high temperature, high pressure fluid will be produced at very high rates of, from the DOE cases, it could be easily more than 20,000 barrels of brine per day. So then the heat and methane can be extracted. And then the CO2 that is captured from power plant can be mixed with that brine and be injected into the same formation. So in this way, we're going to have a closed loop, and the CO2 will be mostly dissolved in the brine when it's injected into the same formation. So in the reservoir simulation study and the calculations that we had, per ton of stored CO2, we can get at least around 5 MCF of gas. And also the gross amount of geothermal energy can be something around 1,500 kilowatts hour per ton of stored CO2, which, as I said, if the temperature is more than 100 degrees of centigrade, it can be used in geothermal power plants. But if it's below that temperature, it's the perfect temperature for a capture unit, because in an amine scrubbing, the reboiler takes a lot of heat at the temperatures of around 200 to 300 degrees of Fahrenheit. So this source of heat can be directly used in the capture plant. So as the opportunities for these types of projects, we saw that very high production and injection rates can be achieved. As I said, more than 20,000 barrels of brine per day for each well, and almost 100 tons of CO2 per well. So, and it's because very large pore volumes and also high permeability of these formations. Also, the pressure control and sweep efficiency will be favorable, because instead of injecting supercritical gas, we are injecting a mixture of gas and brine. So the CO2 is mostly dissolved, and it controls the mobility. And also the risk of leakage is much less, because the CO2 mostly remains dissolved in the brine, and these formations are very deep. But then there are the challenges. These wells are super expensive. Operation is expensive because it's high pressure, high temperature, and they're deep. And also handling the produced brine, the corrosive brine, is expensive, and it can cause scaling in well bores and pipelines. At the same time, if you want to use the heat for capture plants, the capture plant needs to be close to the heat source, because you cannot transport the geothermal energy to hundreds of miles away. The other topic I'm going to have a quick overview is about gas storage and EOR in unconventional shale plays. We know that, for example, in Texas, we have tens of thousands of shale wells, mostly in Permian, Eagle Ford, and Barnett shale. But at the same time, we know we have more than 500,000, by now, we have more than 500,000 shale wells in the United States. So the question is how much the ultimate recovery can be improved by injecting gas and doing huff and puff in unconventional formations, and how much gas can be stored in each well. So far, there has been several studies about huff and puff in unconventional formations. Here at UT Austin at department, we have been lucky to be involved directly in a couple of pilot projects of gas huff and puff in shale formations. For example, in Texas, we have been involved in both Eagle Ford projects and Permian Wolfcamp projects. And the gas injection has been implemented and it's been applied in different fluid types, all the way from black oil to volatile oil and gas condensate reservoir. So we have been involved in the design and optimization and operation of these pilot tests. As you see, for example, for each pad of wells, there need to be one of these gigantic compressors that's like a 3-story building that they can pressurize to 10,000 psi and handle 20 million SCF of gas per day. So in the design and also modeling and simulation, for example, for the Eagle Ford, we were dealing with a pad of 13 wells, and the injection was cyclical, like half in one side and half at the other side, and then switching. So when one side had injection in multiple wells, the other side were producer, and then switching between those two. And these wells were like on the shorter side of 1 mile and spacing of 550 feet. But the problem is that because of the short well spacing in most unconventional formations, there are a lot of frac hits between well bores, which makes the prediction forecasting pretty difficult, because there needs to be good characterization of the frac hits and also the natural fractures, which in our case, we have been using EDFM by Simtech, which is a very powerful source, which can is only source out there that can handle these very sophisticated network of fractures. As a few like main numbers about the cases that we had in the Eagle Ford and Permian, as I said, each compressor can handle 20 million SCF of gas per day and pressurize up to 10,000 psi. So we're talking about large amounts of gas. And as I said, it's very unpredictable about the pressurization because a lot of uncertainty about the fractures. So what we saw, the injection period to hit the maximum pressure that we needed to increase the recovery could be something between 15 days to 150 days for one well to hit that target pressure. And the gas that was needed for each cycle to pressurize could be completely different, somewhere from 100, 200 million SCF to 1,000 million SCF. And but as you see, in almost all the cases, the operation for improved recovery was successful. And in each cycle, we had like a big jump in oil production before doing the next cycle of injection, and again have another jump in the production rates. But all these cases were implemented with field gas, because at the time, field gas is the most available, the cheapest source for operators, especially in Eagle Ford. There's abundance of produced field gas. So we did the same study. What if we do the CO2 instead of the produced field gas, and what will be the recovery and storage? So about the recovery, as you see for this specific case, CO2 was showing a little bit of improvement over the field gas for incremental oil recovery over the time. So in like a 20-year process, you will expect something around 30% to 70% of improvement in oil recovery. And based on the fluid type, CO2 and field gas would compete with each other. But there is always like a slowdown in improved oil recovery over time. Most of the increment happens in the first few years. About the storage, we figured out that CO2 storage, we can store more CO2 compared to the field gas because the density of CO2 is much higher. So for each case, around a few billion SCF of gas can be stored in each well, which for this specific case, for example, it's about 160,000 metric tons of CO2. And the problem is that the storage is always like a cyclical process, and the storage rate slows down over time. So as the opportunity, we know that like storage capacity per well can be a few 100,000 tons. So considering that now there is more than 500,000 shale wells in the US, the in-place capacity now is a few billion tons of CO2. And also we can have considerable improvement in ultimate oil recovery by injecting CO2 in unconventional formations. But then the challenges are that the gas containment and pressure buildup is very unpredictable and needs investment for fracture characterization. Also, achieving sustainable rates is another issue because of the cyclical nature of the process, and also over the time we have to recycle a lot of gas, which is expensive. And pressurization and distribution of gas is another problem because of the large footprint of these wells, and we are talking about shale basins that are very widespread from each other. And as the last topic, I'm just going to go quickly over the project of West Ranch CO2 EOR, which was the CO2 injection, CO2 EOR in a conventional oil formation. The project operator was Hillcore Company, and it was a mature field that was discovered in 1938. And before going into tertiary production, it produced more than 390 million barrels of oil. The CO2 was captured from Parish Power Plant by Petronova Consortium and was piped down 80 miles in a 12-inch pipeline to this oil field, West Ranch, in the Gulf Coast of Texas. As a few facts about this whole project, Petronova was designed to capture about 1/3 of carbon emission just from one boiler of a coal-fired power plant, which is about 1.6 million metric tons of CO2 per year, which is equivalent of capturing CO2 from 240 megawatts output of that power plant. And the capture plant was amine scrubbing, could capture 90% of the CO2 flue gas, CO2 from the flue gas, and the purity of the output CO2 was about 99%. The oil field before starting the injection was producing only 300 barrels of oil per day, but it was expected by injecting CO2 to increase it by a factor of 50 to 15,000 barrels a day and continue the production and injection for 20 years. And at the time, I was part of the Texas Bureau of Economic Geology, and the project PIs were Susan Haworka and Saeed Hosseini. So they helped me a lot through the whole time of the project for me as being in charge of the modeling and simulation. So Bureau of Economic Geology was in charge of monitoring the movement of CO2 in the formation, in the injection formation, and also monitoring the presence of CO2 in the above zone in case of having any CO2 leakage. The project implementation was considered as a success because it was completed on time and on budget compared to the Kemper project that Dr. Duncan was talking about previously that was just imploded a few days ago. And but unfortunately, NRG had to shut down the Petronova project on May 1st because of very low oil prices at the time. Also, there were some technical challenges with the capture and delivery of CO2. There were frequent outages of the capture power plants, which at the end, the sequestration had a shortfall of 17% compared to the target. So as the modeling and simulation, as I said, we were monitoring at the time the pressure and also the movement of CO2. So the injection was happening in one of the production zones in Frio, And then Bureau had pressure gauges in both injection zone and 2 monitoring zones, one in the same Frio formation higher up. And then on top of the seal, there was another monitoring formation, each with 5 different wells and pressure gauges. So for building like a multi-stack model, we had to use about 2,000 well logs in the neighborhood, in the formation to build to find the horizons and also find the porosity and permeability of the formation. And one of the tasks was running modeling and simulation to make sure that especially in the main formation, the pressure doesn't exceed the frac pressure. And as it shows, for example, at the end of first year of production and injection, there were some pressure buildup around the formation in the injection zone, but it never exceeded 3,000 PSI. But as it showed, the gas saturation, the problem with supercritical CO2 is that gas always migrates to the top layer of the reservoir. As you see, there is a lot of accumulation of gas in the top layer when there wasn't much of gas at the bottom layers of formation. So even if like by using like a WAG strategy, still most of the gas was moving toward the upper layers. And as I said, as one of the tasks was to monitor and detect if there is any leak in the upper formations, in the monitoring formations. What we could do at the time, we had the multi-stack models, and the first monitoring model layer was an under-pressured formation, while the top one was hydrostatically pressured formation. So based on all the dynamic of and also the formulation and modeling and simulation, it was showing that the risk of leakage to the under pressure formation was much higher compared to the one that was hydrostatically pressured because of the bigger drive in the delta P that was between the injection zone and also the under pressured zone. So as opportunities, we know that the risk of leakage in this formation is pretty low because of the proven cap rock that has been existed there. And we know that we can have considerable improvement in ultimate ore recovery. And we have this technology has been well established, as Dr. Lake was saying, more than 50 years of experience in CO2 EOR in conventional fields. But the challenges is that always mobility control and sweep efficiency, and also high gas recycling volumes. At the late stages of the project, 70% of the injected gas is, almost 70% is the recycled gas. And at the same time, co-optimization of EOR and storage is always a challenge. The operators for EOR would like to recover their gas because they have paid for that, it's valuable, while at the same time for the storage purpose, you would like to store as much as you can and get it trapped in the formation. So that's it for now, and thanks for listening to my talk. Please, if you have any questions, don't hesitate to ask.
Thank you.
Yes, thank you very much, Dr. Ganjdanesh, for your presentation. We have a couple of questions. Let's see. The first one says, do you have information regarding if the incremental cumulative recovery presented are consistent across different shale plays, or do they vary a lot?
They vary a lot, and it's not necessarily dependent on shale plays. It's dependent on the fluid type. It depends on the depth and the pressure of the formation, how much you need to pressurize. It's a topic. We have seen that in the formations that they initially have higher pressures, the chances and the incremental recovery is mostly higher. And also it depends on how much fractures you have in the place. For example, in Eagle Ford, number of natural fractures were less, but at the same time, most formations are heavily developed. So the fact that well spacings are pretty short, we have a lot of fracture hits. So controlling the gas plume and pressure buildup is not that easy. But at the same time, for example, in Permian, there are lots of natural fractures, which causes a lot of headache to forecast. And yeah, I'm saying that pressure buildup is the main challenge which can change place by place.
Thank you.
Okay, Dr. Ganjdanesh, we have one more question, and that will be the last one because of time. It says, if a reservoir contains solution gas with high CO2, about 60%, do we still have the benefit of CO2 EOR?
I would say that it's killing the advantage of CO2 because CO2 is already in place. So you are not one of the advantages if you're talking about the CO2 EOR is that CO2 has very high miscibility with hydrocarbon in place, and the target, the MMP, is higher between CO2 and hydrocarbon versus, for example, natural gas or methane. So if you're already having CO2 in place, you're not going to improve like by adding CO2. So it's just my intuition.
Yes. So thank you very much, Dr. Ganjdanesh.
Thank you.